Hello, and welcome to another lecture in the course. So we're going to look at why the holomorphic derivative is holomorphic. We're going to get another Cauchy integral formula for the derivative, actually. And we're going to prove Morera, which is a converse to Cauchy, and we're going to use what we know about derivatives for that. So the last time we proved that holomorphic functions are analytic. So let's restate a theorem that we proved for analytic functions, and let's restate it for holomorphic functions. We have a holomorphic f defined in an open set, then f is infinitely complex differentiable, right? We knew that for analytic functions, but now we know that analytic functions or holomorphic functions are one and the same, right? In particular, we know that f prime, the derivative, is holomorphic. That's a little weird, right? We have a function, and if it's differentiable, then the derivative is differentiable, and its derivative is differentiable, and its derivative is differentiable. Just by having that first derivative, right? I mean, nothing like that is true for a real differentiable function, right? Functions that have a real derivative, like functions on the real line. Let's say, you can start with any continuous g, and a continuous function need not have a derivative at any point, right? And it's easy to have that example that it doesn't have a derivative at one point, but there's actually a way to construct a function which is not differentiable at any point whatsoever. It's still continuous. And that can be a derivative of a function, right? I mean, I apply the fundamental theorem of calculus, right? So that means that just having a derivative doesn't really say much about a derivative, right? And the derivative doesn't even need to be a continuous function. There are functions whose derivatives are not continuous, right? Not every function is a derivative, but right, quite a few functions are real derivatives. But for holomorphic functions, no. If a function is holomorphic, its derivative is holomorphic, right? Now, this is something that maybe was gonna would freak out a calculus student. In complex analysis, integrating and differentiating are kind of the same thing. We differentiate by integrating. Integrating is easier, right? Except in calculus. Calculus is harder, but anywhere else it's easier. Oops. So if we start with a holomorphic function, and we start with a disk whose closure is contained in the domain of f, right? Then for any k, the kth derivative, and z is going to be a number in any number in the disk, in this disk, right? So this is basically a Cauchy integral formula for derivatives, right? So the kth derivative of f has a formula that looks very much like Cauchy's formula, right? It's again an integral over the circle. It has an f in here. Instead of zeta minus z in the denominator, well, there's that k in here, right? So you take the k plus 1's power, and then there's another difference over here. You have k factorial, right? But other than that, it looks very much like the Cauchy formula, and actually we get it from the Cauchy's formula. We just differentiate the Cauchy formula. All right. Now, let's prove this. So we start by using what we proved, right? We have a holomorphic function. It's analytic, and we know that analytic functions are infinitely differentiable, complex differentiable. Therefore, all complex derivatives exist, right? That means that we can compute them by applying the Wertinger operator, the d by dz, which really is this formal operator, which is this definition over here in terms of the x and y derivatives, right? Where x and y are the real and imaginary parts of z. Now suppose that this conclusion, so we're going to prove it by induction. Suppose that this conclusion, this formula holds for some k, some fixed k, right? And it definitely holds for k equals 0, because for k equals 0, this is just Cauchy's formula, right? When k is 0, the 0th derivative is just the function itself, right? So we have our base case already, right? So now let's suppose it holds for k, and we just need it to hold for k plus 1, right? And let's fix some z in the disk, right? And so we're going to look at the k plus 1th derivative of f at z. Now that is just the Wertinger operator applied to the kth derivative, right? It's not that it is that, it equals that, right? That's another way of computing the derivative, is to apply the Wertinger operator, right? So we apply it to the kth derivative of f. All right. Well, we know that this formula holds for k, right? So we stick that into, we replace the kth derivative with that integral formula. All right. And now we pass these derivatives under the integral, right? We'll say a little bit more about this in just a moment, but let's just suppose that we can, right? If we could do that, then notice that the z derivative, well, it doesn't really care about this this f of zeta, right? Because it's differentiating in z, right? So there's no z here, right? So that's just a constant as far as the derivative is concerned. And so it only falls on this kernel over here, right? And, well, that guy is holomorphic, right, in z. It's just a rational function, right? We can just, it's just calculus, right? Calc 1, right? To take this derivative, just a power rule, right? And if we take this derivative, we're going to, get another k plus 1 coming out. And, well, there would be a minus k plus 1. But fortunately, there's this minus, it's zeta minus z, right? And so when I'm differentiating it in z, that, the chain rule kills the minus sign, right? So I'm just multiplying the k factorial by k plus 1, which gets me k plus 1 factorial. And the power goes down, so it's negative, so it goes, it becomes k plus 2 over here, right? Which is precisely what I wanted. Now, how did we pass the Wertinger operator underneath? Well, we're really passing these guys, right? I mean, we're really taking the x derivative, the y derivative, we're passing those in, and then we're using linearity, right? So if we can pass the x and the y derivative, we're good. So that's just the Leibniz rule, or there's a bunch of these rules, differentiating under the integral. But we can just use the Leibniz rule here, right? The thing for the Riemann integral, because if we take the x and the y derivative, if we replace z with x plus iy, then the x and y derivatives of this thing, those are just continuous functions, right? And so that's good enough for to apply the Leibniz rule, right? It's really because we're again the f zeta doesn't really matter here. It's really this guy, right? And that's a really nice guy. in terms of x and y, right, automatically. All right. And it's, maybe just to emphasize, it's a continuous function of two variables, right? Z and zeta, right? So Z is varying in the in this disk, right? And zeta is varying, well, where the integral is, right? And so zeta is on the circle, right? So zeta minus z is never zero, right? So that's why we're getting nice continuous, right? The even the derivatives, right? Now let's mention the result that will be useful later, which is just an exercise to prove, but it's a bit subtle, right? So suppose that I have a continuous function of z and t, right? Where z is varying in some open u and in the complex plane, and t is just some real real variable varying in some interval ab, right? And let's suppose that for every fixed t, the function f of zt for a fixed t, so just the function of z, is holomorphic, right? Then the first thing to prove is to show that the derivative, and so this is the vertical derivative, right, which is just going to be the derivative of this holomorphic function, right? That's a continuous function on, as a function of both z and t, right? As a function of both variables, right? I mean, we know that it's a continuous function for any fixed t, right? But that it is a it's a continuous function of both variables, right? And from that, prove that the x derivative and the y derivative are also continuous, which is not quite immediate from this being continuous, but if that is that is continuous and f is holomorphic in z, that's going to follow, right? So that means that you have that the x and y derivatives are actually continuous functions of z and t. Now, just to show you that this is not something that should be somehow immediate, is not true for real differentiable functions. If I have a function, so let's just take a simple example. Let's just suppose that I have a function f of two real variables, x and t, and I define it as t times sine of x over t for t not equal to 0, and when t is 0, I'm just going to let it be equal to 0, right? So you can prove that f itself is continuous function on all of R2 on the plane, right? Of two variables, x and t, right? It's a continuous function, and for each t, there should be a comma out here. Sorry about that. And for each t, the function as a function of x, this is differentiable, right? So that's not hard to prove. But that derivative, if I take the derivative, which is just going to be the x partial derivative, that's not a continuous function of both x and t. And you can just compute it, what it is. I mean, for t equals 0, it's clearly 0, right? And for t equals not 0, then you just differentiate this in t, right? And you're going to get something that's not a continuous function of x and t, right? So this is something special about, holomorphic, about complex derivative, right? Now, let's prove Morera's theorem, which is actually a very useful converse to Cauchy. It's very easy to check. Well, maybe very easy, but it's often a useful way to check that a function is holomorphic, but it's easier to integrate, right? So suppose that we have a continuous function f, and suppose that it's the integral over any triangle that's contained in U, and by that we mean the solid triangle is in U, but we're integrating over the boundary, but we want the entire triangle to be in U. So if this is true, then f is holomorphic, right? So we had the opposite before, right? We had that if we had a holomorphic f, then this thing was true for every solid triangle in U, right? So it's basically a converse of the Cauchy for triangles. So this is just the application. It's much easier to integrate a continuous f than try to differentiate it. Now, holomorphicity, the property of being holomorphic, is local. So that means we only have to show this theorem in each neighborhood. So in a neighborhood at every point. So if we want to show that it's basically complex differentiable at some point, well, pick a neighborhood of that point. You might as well have assumed that that's a disk, right? So pick a disk, right? And so without loss of generality, you could assume that U is a disk. Now a disk is star-like, right? And this hypothesis that we had that the integral over all these triangles is 0, well, that was precisely what we used to show that f has a primitive. That was a proposition that we proved, that if this is true for every such triangle in a star-like set, then we had a primitive, right? So that means that there is a primitive in U as long as U is a disk, right? So there's some capital F such that capital F prime is little f, right? All right. So now this is where we use what we've just proved before, that the derivative is holomorphic. So little f is a derivative of this big F, and therefore it's holomorphic, right? Seems to be a little bit of a roundabout way of getting it, but hey, it works, right? So because this little f has an antiderivative, has a primitive, therefore it is a derivative, at least in a disk, right? And therefore it's holomorphic, right? And now you can just do it in any disk that's contained in U. Now, the reduction to a disk is necessary, right? You can't just having a primitive this proposition that we proved before that gave us this capital F, that only works in, well, maybe not only in star-like, but it works only in certain domains. Well, we'll see the simply connected domains, but in that version of it, that was for star-like domains. So, for example, 1 over z does not have a primitive in the punctured plane, right? Actually, I mean that's a big deal. That's that thing that should be the primitive. That's the logarithm, right? But it does satisfy hypotheses of Morera, right? Because, well, you don't have to go, the triangle is never going to go around 0, where you wouldn't, if you did that integral, you wouldn't get 0. But if the triangle is completely contained in the punctured plane, so the triangle does not include 0, then you could, then when you integrate, yeah, you do get 0, right? That's just Cauchy's theorem, right? So that means that you wouldn't always, it's just because something satisfies the hypothesis to Morera doesn't mean that it is an antiderivative. So we needed to do that reduction to, a simpler domain, to a disk or anything star-like, right? So you can't always do it in all of you. You have to do it maybe, in pieces. All right. Now, a typical application of Morera is something like the following exercise. That is sort of a typical exercise in any section of Morera in a book on complex analysis. Start with a continuous function on C, and suppose that it is holomorphic outside of the real line. So on C minus R, it's holomorphic and it's continuous everywhere. Show that it's holomorphic everywhere. Right, and there's other versions of this. For example, you could start with, well, suppose that you have a function defined on some sort of a, maybe punctured disk or something, and it's continuous at a point and holomorphic outside. Then by Morera again, you would get holomorphicity. So there's a bunch of sort of similar exercises. So if you're starting with something continuous and you have holomorphicity in a large enough set, you can use Morera to show that you actually get holomorphicity, right? So that's sort of a typical simple application, typical example exercise. Something like that would be on a qualifying exam. It's a typical thing to put on a qualifying exam, something like that, right? All right. So next time we'll look at the maximum modulus principle. This is one of the other big important theorems in complex analysis. One of my students made fun of me for always saying that whenever he had a question about complex analysis, I just said, "Oh, it's just the maximum principle." So you can solve anything by just applying the maximum principle. So that's what we're gonna prove next time. Look at and prove. All right. So see you then.